All right, we have a fully charged 5.5 microfarad capacitor. It's connected in series with a that resistor. What percentage of the original charge is left on the capacitor after that long of discharging? Okay, this one we haven't actually talked about, but let's do this real quick. So we have a CR circuit. So basically it's a circuit, at least in this problem, there's no battery in it, but there's a capacitor and a resistor, right? So we have, here's our picture. All right, and this is 5.5 microfarads, and what was the other one? 1.7 times 10 to the fifth. That's not a small resistor. Okay, they actually do this in the book. And normally in the book, whenever you have specialized things, they say, hey, you should just look in the book for the formula. And that's probably what I should say to Cindy anyway. But I kind of want to work this one out anyway. So if I can get my pen to start working. So the first thing I'm going to do once my pen starts working is to put C on capacitance and R on resistance and work this problem in general. But okay, there we go. So C for the capacitor, R for the resistor. Okay, what do we know about so we said when you have a closed circuit, basically all the voltage drops have to add up to 0. So we know the voltage across the capacitor, well, C is Q over V, right? And what do we know about a resistor? Well, we know that for a resistor, V is I times R. Right? So let me just get V by itself in the capacitor one. So V is Q over C, and V is I times R. All right. Well, what's kind of weird about this, if you think about what's going on, initially all the charge is on the capacitor, at least in this problem. There is no current, right? So initially there's not going to be any voltage drop across the resistor. It's all going to be coming off the capacitor, right? But then as the capacitor starts discharging, this Q is going to be going down, this I is going to be going up. Right, so gradually we're losing charge on the capacitor and gaining current through the circuit. Well, what that means is that neither one of these numbers are actually staying the same. So the first thing is, at least in this book and in a lot of books, whenever they want to say current or resistance, but they're not constant, and to say they're not constant, they rhyme with a small case letter instead of capital. So first thing we're going to do is say, well, really this is not constant, so it's Q over C and I times R. And then the second thing we want to think is, okay, well, we've got two different things that are changing. We got charge and current. How are they related to each other? Well, what was current to begin with? It's how fast charge is moving, right? So I'm going to say something that's going to make sense to Colby. So that means that what current really is dq dt, right? So our actual equation is going to be that the voltage drop across the capacitor should be the same as the one across the resistor. And of course, I always get signs wrong, but if you do it this way, it's going to blow up. So apparently there should be a minus sign in here. So let me do the usual thing of getting the derivative by itself. So again, I'm sorry, this is not going to make a bit of sense to half of the room, but so you can wait for the final answer here in a second. All right, so the derivative of Q should be some number. So this number is not changing. I mean, the resistance of the capacitor is what it is. Or sorry, the resistance of the resistor, the capacitance of the capacitor, those are two numbers set in stone. But the only thing changing is the Q. So Kobe, what function, if you take the derivative, you just get a number times the function you started with?
What are you talking about?
So think back to your calculus class of all the functions you have learned and loved.
Okay.
There's one of them that when you take the derivative, either nothing happens or at worst, just a number pops out front. We are recording, aren't we? Yes, we are.
On my calculator, on the page, and I can get it up on my head.
Okay, so e to the x, you take the derivative, nothing happens, right? Or more generally, you basically have q of t is some initial q, and then e is the minus 1 over rc t. So, and that is what Cassie should write. Not Cassie, Cindy. Cassie's not in this class. Okay. So what happens whenever you, and I'm going to go ahead and do the current too. So the current's going to be the same formula.
I should have known that.
Is the initial current times, actually it's not. Well, sort of. Okay, apparently I'm.
The E, that's function E.
Yeah, so it's e to the,
Okay.
yeah, that's like e to the x or whatever. Oh, okay, yeah, so I was grabbing it wrong, which makes a whole lot more sense now. I said that earlier and I was like, that doesn't make sense as I was saying it. But no, initially you've got a lot of charge and the current is running like a lot, I guess. And then as it dissipates, they're both going down. You don't have as much charge on the capacitor, and then the current gets weaker and weaker because if you take t goes to infinity, both of those go to 0.
Only have a T on both sides now.
Oh, this is like function, like q at time t is given by that.
Gotcha.
Okay. All right, and this 1 over RC is not being written on my page. The 1 over RC is called like the time constant of the circuit. I mean, it's more of a math thing. So let's go back to the problem now. So the problem says, okay, here's our C, here's our R. So the first thing we're going to do is just multiply them together. So I need, I don't care what's new, 5.5 times 1.7. And let me actually put 0.17 because one's 10 to the minus 6, one's 10 to the 5th. So, okay, you get 9.35. That's R times C. 1 over that and negative. All right, so that's negative 1 over RC. And then times the time, so times 1.5. And then I want e to that. So what that says is that after 1.5 seconds, both the charge and the current will be down to 20% of where they started. That's that. Basically all I did, I evaluated that e to the negative RC over negative 1 over RC t. So I got 0.201, so it says, hey, either one of them, doesn't matter if you ask about charge or current. You're going to have 20.1%
What was
left.
that I?
The I?
In the formula, what was the I?
Okay, let me go back. Okay, so the little q, maybe I should put zeros on here just to make it more clear. Okay, so this says the current at a particular time, or the charge at a particular time is whatever the initial charge is times this E guy. And same thing with the I. The current at any time is whatever the initial current is times this E guy. And as far as that goes, you could get
So all they wanted to know was the E.
yeah, that's all we did for this one.
They didn't give it crap what the number was.
Yeah, as far as that goes, you can also get the relationship between the initial current and the initial charge just from the derivative. The initial current would just be Q naught over RC, because when you take the derivative, that thing pops out. But yeah, anyway. All right, so that was really easy once we had the formula, wasn't it? Yeah.
It's like way too easy. That'd be one I get wrong.
Yeah, you had a tendency to get the easiest ones wrong. It's like, it's got to be harder than this. No, it's really not. You need confidence to Trey. All right. As initially, okay. So now we have the same sort of thing, but we have a battery in there too. So I could work it out. I mean, basically, it's almost the same thing. You're going to get an exponential plus a constant term is the only difference. But let me actually just look it up in the book rather than work it out, since I don't want Cindy to be too bored with me. We already spent a good chunk of the day talking about Lincoln, so.